Good morning guys, Anjani Kumar here, dealing instrumentation subject for a final year electrical students, right? In the last session we started different types of digital voltmeters, right? In that we successfully discussed about counter type digital voltmeters, right? So now we are going to discuss about successive approximation type digital voltmeter, right? Second concept is successive approximation type digital voltmeter. So why we are implementing this means, so you know about the counter type digital voltmeters require a clock pulses are very high. So 2 power n minus 1 clock pulses that we required. Right, but suppose if it is a 3-bit, so definitely almost 7 clock pulses that you require. For a 4-bit, almost 15 clock pulses that we require. So number of clock pulses is required. It's time consuming process, right? If you want to find out the output voltage 4, there will be 4 operations has to perform 0, 1, 2, 3. So after that, at the end you will get the result. So like this, the number of clock pulses is very high. In order to reduce this time consuming, so we implemented the concept called successive approximation type digital voltmeter. Now we'll discuss about the block diagram. So after that working, and with an example we will finish, right? Simple. The block diagram is similar to the counter type digital voltmeters, right? Same patterns what the counter type is having. This is AND gate, so which is converted to connected. It is a comparator. So this is the clock pulses that you applied here, right? So now in n-bit counter, in a counter type digital voltmeter, so we are using n-bit counter. So but in a successive approximation, we have a successive approximation resistor, right? So SAR means successive approximation register. Alright, so whatever the digital which is converted to digital to analog counter here, so this is called BD, the output of digital to analog converter, and whatever the input that you are giving here, right? So the comparator, this is a comparator, will check, right? This is a logic gate. Right, so this is a logic gate, not the AND gate. So it's a logic gate, right? So this is the binary data, right? Simple, nothing is there. Similar construction, but one important thing, one important block that what we are going to discuss is successive approximation register. That's it. Now we will discuss first what is a successive approximation register. If you know this, all the things, you know everything, right? So how the comparator will operate, how the comparator will work, how the digital and on what basis the digital to analog converter will work, and logic gate will work, you know everything. Now the main function of this successive approximation type digital voltmeter is to reduce the number of clock pulses and reduce the time consuming, right? See, so working of successive approximation register. Approximation register. The function first, so the register at first it will set MSB bit to 1, right? If you consider a 3-bit bit, I am considering 3-bit data, right? Whatever the digital form that we are getting at last, that is a 3-bit. In that 3-bit, one is MSB, so another bit, another LSB. Last bit we can call it as LSB. At the time of starting, your successive approximation register will make the first MSB bit is set. So it can set the MSB bit. First point is, first it can set the MSB bit, right? First I'll write down the forms, right? After that we will discuss with an example. It will be understand clearly, right? So first I'll write the clear notes, so then only it will be helpful for you, right? The first, it can set the MSB bit. Set means it will make set means 1, reset means 0. That's it. Second one, right? There is a comparator na. So if V in greater than VD, right? If V in greater than VD, so it can set the second bit. After setting, again it can set the second bit. Set the second bit, right? And third, if V in less than VD, right? Here the typical nature will come. It can reset the previous bit and set the next bit. Reset the previous bit and set the next bit, right? First I'll write it down. I will read it out. Then only you will 50% idea will come out. With an example it will be clear. So the working of a successive approximation register, the first, it can set the MSB bit 1. It can set the MSB bit. Next, there will be two possibilities. First possibility is if V in greater than VD. So definitely there will be two possibilities, either V in greater than VD or VD greater than Vn, right? Either V in greater than VD. So then it can set the next bit, right? It can set the next bit, okay? If V in less than VD, you know about VD. VD is nothing but digital to analog converter output, right? If V in less than VD, right? So what happened? It will reset the previous bit and set the next bit. That's it, right? Reset the previous bit and set the next bit. We will see the algorithm with the 3-bit explanation. So with it, you can clearly understand how the working and all these things. So I'm taking a 3-bit nature, alright? The first thing is, first SAR 3-bit na. The first point is SAR will set the MSB bit, right? So first is 0 0. You thought that 0 0 0, right? So first point is it will set the MSB bit, right? So set the MSB bit means 1 0 0. Okay, it is setting the MSB bit, right? Here you will get the two options, right? The first option is V in greater than VD, right? And second option is V in less than VD, right? If V in greater than VD, so what is the function? it will set the next bit also, right? It will set the next bit. So again 100, so one bit already set, right? It set the next bit. So what is the next bit? 0. It can set, right? Hope it's clear. Point is, if V in greater than Vd, it can set the next bit. That's it. The next bit is 0. I'm setting the next bit. You don't want to take a chance on the previous bit, right? And another one, if V in less than Vd, so what is the function? It will reset the previous bit and set the present bit, next bit, right? If we'll reset the previous bit is 1 na, so 1 ni reset cheyala. Then it will set the next bit ni set cheyala. Hope it's clear. I just want to explain one more time. Is if you take the 3 bits, the starting is 0, 0, 0. So what is the function of successive approximation register? It will set MSB, right? Starting, it will set the MSB. That's why 1, 0, 0. After that, there will be 2 possibilities, right? If V in greater than Vd, V in less than Vd. The function is same. Whatever the counter type of function is similar, right? If V in greater than Vd, it will set the next bit. Next bit ni kuda set chesesam. If V in less than Vd, it will first you will reset the previous bit and set the next bit, right? It will reset. Previous bit is 1 is setting now. It will reset the previous bit and set the next bit. Same thing, right? Again you will get 2 possibilities, right? So here also V in greater than Vd. Here also V in less than Vd, right? So you will tell the 2 possibilities, right? If V in greater than Vd, so what happened? You will set the next bit. So here this bit you set in a previous thing, you will set another bit, right? So 1, 1, 1, right? So you are setting the next bit, that's it. If V in less than Vd, you can reset the previous bit and set the next bit. So that means you can reset the previous bit. So what is the reset previous bit set chesindi 1? Danni reset cheyala. Then set the next bit. Hope it's clear. Nothing is there, right? Reset the previous bit. Previous bit 1 set chesunava, danni reset cheyi. Next bit ni set cheyi. That's it. Nothing. Again here also 2 possibilities. Right? So what is the possibility? V in greater than Vd. V in less than Vd. Right? Definitely there will be 2 possibilities, right? Right? Tell me. If V in greater than Vd, right? The next bit you are going to be set. Right? Whatever the set bit is set. Here is the set bit now. The next bit is set chair. So 0, 1, 1. Alright. So if V in less than Vd, whatever the set previous, it will be reset and next bit you will set. So previously set chesinindi this bit. You have to reset this bit and set the another bit. So you have to reset this bit, reset this bit and set the another bit. Hope it's clear. Again you will get 2 possibilities. Again you will get 3 possibilities, right? V in greater than Vd, V in less than Vd, right? Right? See, if V in greater than Vd, right? Set the another bit. You have any another bits? No bits. You just remove this. You just as it is. You don't have any other bit to set. You just make as it is. Right? What is V in less than Vd? So what happened? You reset the previous bit and set the next bit. Previous bit ni reset cheyala. Right? This bit is a previous bit. You have to reset this one and set the next bit. You don't have any set bits. I just want to remove. That's it. Hope it's clear. Previous bit na set chesinది 1 kada. So you have to reset win and set the next bit. Next bit set cheyadaniki ఇంకో bit లేదు నీకు. That's why you have to leave it. Right? Similarly, you have two things over here. V in greater than VD, V in less than VD. Alright, so you have to make this one. Alright, see, if V in greater than VD, you have to set the next bit. Right, so you have to set the next bit. Is there any next bit to set? Only 3 bits is there. Next bit you don't have any set, so just leave it. Alright, so V in less than VD, you have to reset the previous bit and set the next bit. Whatever the previous bit 1, you have to reset it. Next bit ledu, so just remove. So 1 0 0. Right, reset. Set cheyadani ingo bit ledu naku, that's why I just leave. Here also you will get two things. That is V in greater than VD, V in less than VD. Right? How many bits that you have? Right? So V in greater than VD, that means you have to set the next bit. For setting, there is no bits to set. Only 3 bits. 0, 1, 1. You just leave it. If V in less than VD, you have to reset the previous bit and set the next bit. Previous bit is 1. You have to reset it. Next bit don't have any bits. You just leave it. 0, 1, 0. Hope it's clear. Right? Again, you are getting two possibilities. Right? Simple, it's an algorithm approach. So if you know the algorithm, the working is very easy. V in greater than VD, V in less than VD. Right? So V in greater than VD, the next bit you are going to set 1. Right? Right? Is there any bit to set? No. You just leave it. You just same as it is. Ingo bit ledu no reset set cheyadaniki. If V in less than VD, reset the previous bit and set the next bit. Next bit set cheyadaniki em ledu, but reset cheyochu previous bit. Previous bit endi 1. You have to reset it. 0 0 0. Right? So this is a 3-bit algorithm. Right? See how many clock pulses that you required. So that is nothing but it's a 0 1 2 3 4 5 6 7. Right? You know, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 triple 1. So you are getting 0 1 2 3 4 5 6 7. So for the entire, how many clock pulses you are having? So this is 1 clock pulse, 1 clock pulse, right? So this is another clock pulse, this is another clock pulse. So total for a 3-bit, how many clock pulses that you are having? Only 3 clock pulses, right? 3-bit, 3 clock pulses. For a 3-bit, 3 clock pulses. In the 3 clock pulses itself, you will get the result. Right? So for n bit, how many clock pulses? Only n clock pulses. In the case of counter, you are having a 2 power n minus 1 clock pulses required each and every time. So it's a time consuming process, and each and every time generating a clock pulses is very difficult. Right? So nothing is there. I don't want to explain one more time because it's a clumsy process. Right? If you want to really, if you want to understand, you just rewind the session, and definitely it will be understand. Nothing is there. Initially, your successive approximation register will set the MSB bit. Next, it will check the condition. If V in greater than VD, right? It will set the next bit. That's it. Doesn't affect on previous bit. If Vn is less than VD, right? You can reset the previous bit and set the next bit. That's it. Those 2 things that we did. the entire algorithm approach. Now the concept is clear. Now we will move to the block diagram approach. Right? I hope the algorithm is clear for you. We'll move to the block diagram approach. Right? So initially, per suppose if you want to find out what's the value 5, if you want to find out the 5 volts, hope it's clear, right? If you want to find out the 5 volts, right? So whatever the input that you are giving to the comparator, which is a 5 volts, right? The first SAR, what the function of SAR? It will make a MSB bit. It's a 3-bit now, so it will make MSB bit 1 0 0, right? So it will make 1 0 0, right? So what is the value of 1 0 0? You know that 1 0 0 means 4 now. Hope it's clear. 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0, right? 1 0 0 is nothing but 4. So what is the value of this one? Is nothing but, see, initially the function of successive approximation register make your MSB should be set bit. So you will make MSB set 1 0 0. So what is the digital to analog form? So what is that value? The value is 4 here. Correct? So value is 4. You will check whether V in greater than VD. So yes, V in greater than VD. You know V in, that means 5, which is greater than 4. Is it true? Yes. If V in is greater than VD, true na? So definitely what is the value? This is a 4. Right? So if V in greater than VD, that means 5 greater than 4. Right? What you should do? You should make a next bit. You will set the next bit. So what is that next bit? I'll explain with this here itself. Here itself, right? The first so 1 0 0 SCR will set 1 0 0. Okay, what is that value? This value is 4. So what is the V in? V in 5 greater than 4. Is it true or not? So definitely true. If it is true, means you have to set the next bit. So what is the next bit? This 0, second bit. You have to set that one. So you have to set the next bit. That is 1 1 0. Right? So what is the value of 1 1 0? So 1 1 0 means 6 na. 1 1 0 is nothing but 0 0 0 0 0 0 1 0. You know 1 1 0. What is the value of 1 1 0? Its value is nothing but 6. Again you have 2 options, right? Is it V in greater than 0? V in greater than VD? No. So what is the V in? 5. 5 greater than 6? Definitely not. That means V in less than 6. So you have to make this one. You don't have this option because this is wrong. V in greater than 0, this is wrong. So this option is correct. So V in less than VD. If it is less than, what you have to do? Right? So previous bit you have to reset and set the next bit. Right? So previous bit enti 1. 1 you have to reset and set the next bit. So what is the value? 1 0 1. Right? So 1 0 1. Right? What is value of 1 0 1? So what is the value of 1 0 1? It's a 5 now. So 1 0 1 is 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 is nothing but 5. So what is the value of 5? Right? See, V in equal to VD. Is there any comparison? So there is no comparison. What is the output of comparator? There is a comparator output is 0. So what about the AND gate? So definitely there will be no result from the AND gate. So then successive approximation will display the result as 1 0 1. The result as 1 0 1 in your display screen. Hope it's clear. I'll clearly explain one more examples, right? So I just want to explain one more time, because it's very difficult. First you have to understand the algorithm, so then only it will be very easy for you to understand the working of successive approximation register. So what is the function of successive approximation register? If you take a 3 bits, first MSB bit will be set. Next you have two options. The first option is V in greater than VD. What is VD? VD is nothing but digital to analog counter output. Right? If is V in greater than VD, definitely. So whatever the your MSB bit is set now, you have to set the next bit. If V in less than VD, you have to reset the previous bit and set the next bit. That's it. Those conditions that you have to understand. Right? I'll explain one more time. Right? So whatever the V in that you are taking 5 volts, right? See, V in is 5 volts. 5 volts you are taking, right? Now first function of successive approximation the register is, it is a 3-bit now. The first bit you have to set. So 3-bit means it starts from 0 0 0, but successive approximation register, it will make a set the MSB bit. So first bit is 1 0 0 1 0 0. Hope it's clear, right? 1 0 0. What is the value of 1 0 0? So 1 0 0 is nothing but 4, right? You have two options, right? The first option is, so V in greater than VD, V in less than VD. See, what is my V in? V in is equal to 5. See, 5 greater than 4 now? Yes, 5 greater than 4. 5 greater than 4. Yes, it's true. So then what should you do? You have to set the next bit. So what is the next bit? 0. You have to set the next bit. 1 1 0. Here also, so what is the value of 1 1 0? So 1 1 0 is nothing but 6. You know 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1. So it's a 0 1 2 3 4 5 6 7. So what is 1 1 0? 6 value. Here I will get the two options, right? The first is V in greater than VD, V in less than VD. So what is the V in? 5. What is the 6? 5 is greater than 6 or less than 6? It's a less than 6. So this option is going to true. So you have this thing, right? What is the less than? V in less than VD? You have to reset the previous bit and set the next bit. So what is the previous bit? 1. 1 you have to reset it and set the next bit. So 1 you have to reset and set the next bit. That's it, right? Then you have two options, right? So what is the value of 101? So 101 is nothing but 5. You will get V in greater than VD, 5 greater than 5 or 5 less than 5. That means V in is equal to VD. If these two comparators, V in is equal to VD, is there an output? 0 set. Then what about the AND gate will show? There is no result. AND gate won't work. Then the SCR will show whatever the result there 101. It will be displayed on the screen. So what is the value? 101 is a digital. So what is analog form? That is called 5. So 5 is converted to analog form, right? I hope it's clear. It doesn't require any time. If you go for a counter type, you just start from 0 1 2 3 4 5. So how many clock pulses? 2 power n minus 1 clock pulses that you required. So it's very difficult. For this you directly enter into the 4, just single step you'll get the result. Right? So what is the function of successive approximation registers? Means whatever the drawbacks that coming out from the counter type is going to be eliminated with the help of successive approximation type digital voltmeter. In a counter type, the number of clock pulses is 2 power n minus 1. In a successive approximation type, the number of clock pulses are n. If it is n bit, there is n clock pulses, right? If it is a 3 bit, only 3 clock pulses is there. See, only 3 clock pulses, right? in a 3 clock pulses, you will get any form. In a 3 bit digit, any of the thing that you will get, right? I hope it's clear. So this is a clear explanation regarding successive approximation type digital voltmeter, right? So I don't want to explain 2 or 3 times. If I explain 2 to 3 times, it will be clumsy, right? Somewhat difficult. If you want to really understand, definitely rewind this video and clearly analyze, right? So nothing is that simple concept. It's very, very important concept, right? Thank you for now. In the next session, we will discuss about ramp type digital voltmeter. That is very, very important concept. Hope it's clear, right? Thank you for now. In the next session, we will discuss about ramp type digital voltmeter, how it will work, and the block diagram. Thank you for now.